All right. Good morning, everyone. Thank God it's Friday. So, um, we'll get started here. I apologize. I just realized that I didn't have the PowerPoint slide made visible to you guys. Because on Wednesday, usually what I did is right after this class, I'll made it visible to you guys. But on Wednesday, because in the morning I was home and then I had to rush to campus for the lab in the afternoon, so then I forgot it. But I apologize for that. Okay, um, so to start with today's lecture, again, the reminders items now will be homework 9 due in the coming Tuesday. Okay, so it's only a few days from now. I think a couple of you guys actually have finished it, and then um, a few more have started. So if you haven't get started, make sure you get started over the weekend. Okay. And then again, the exam 3, still tentatively, it's going to be next Friday, but we'll see if, so on Monday, the academic affair is going to determine if we are going to continue to be online or resume the in-person lecture. But so then on Tuesday, we should have the information about that. Okay, so again, we can talk about if we have to postpone exam 3 on Tuesday then. But that's the current plan still. Um, so today we are going to check the reminder of chapter 11. Okay, so we'll start with the second section in chapter 11, angular momentum. So this is again kind of the analog to what we learned in linear motion. So we'll start with comparison of the angular momentum to linear momentum. So in linear momentum, it's linear momentum is defined as mass times velocity, p equals to m times v. So then in angular motion or rotational motion, the angular momentum, we can take the same approach. So the angular momentum should be equal to moment of inertia, which is the counter quantity for mass in rotational motion. So that will be that moment of inertia times the angular velocity omega. Okay, so it will be moment of inertia times angular velocity. The SI unit for angular momentum is kilogram times meters square over second. Because moment of inertia has the SI unit of kilogram times meter square. It's like mr square, right? And then for angular velocity omega, it's the radians per second. So you can say kilogram times meters times radians times per sec divided by second, or you can just say kilogram times meters over second, because radian is dimensionless. Okay. All right. So we will take a look on the simplest system for a point mass if it's rotating with a x rotation. So then from its definition, angular momentum should be equal to moment of inertia times its angular velocity. For a point mass, the moment of inertia is equal to mr square, the mass times its distance to the x rotation square, and then angular velocity is equal to linear velocity divided by r. Okay, so then combine these two expressions together, you can see r here, down here in the denominator will cancel out the square. So you will have mrv remain, or r times mv. Okay, so m times v will be the linear momentum of p. So then angular momentum should be equal to the radius times the linear momentum p. Okay, so L in relationship to p is again similar to the other quantities we learned earlier in rotational motion in relationship to the linear motion. Okay, so it's r times p. So this is the case when the r and then p, or the velocity, is in the tangential direction. Now, in general, sometimes the v is not in the tangential direction. So for example, in the figure shown on the right here, the mass maybe a certain moment is going actually in that direction. Okay. So if that's the case, then you'll take the angle between r and p. all right, and then you'll be doing sine of theta. Okay, so L is equal to R times P times sine of theta. So basically, you're going to take the component of P that is perpendicular to the R vector. Okay, and then the one is parallel to it actually doesn't contribute to the angular momentum. Okay, so in general, L is equal to RP sine of theta. Theta is the angle between I and the V or P. Okay, because V and P should be having the same direction. All right, now that's the magnitude. So magnitude of L equals to R times P times sine theta. For the direction angle, for the direction of the angular momentum, so that's defined as R cross multiplication of P. So then you can use your right hand rule to determine. Okay, so if I and P are in the XY plane, then use your right hand rule. It's going to be in the Z plane. Okay, in the Z direction for the angular momentum, the direction of it. Okay, so that's the cross product of these two vector R and P. Okay. All right, so we'll take a look one quick example. I think on this one should be easy. So find the angular momentum of a 16.0 gram DVD considered to be a uniform disk of radius 6.00 centimeters spinning with an angular speed of 125 radians per second. And B, a 125 kilogram motorcycle driving with a constant speed of 8.92 meters per second on a circular track of radius 35.7 meters. Okay, A, it's a disk. So a disk has a moment of inertia of 1/2 mr square. Okay, so we'll treat it as a uniform disk will be 1/2 mr square. This is the quantity. You can actually look it up from the table. Okay. On the second part, we are going to treat the motorcycle with as a point mass. So you're going to use two different expressions for the angular momentum. The first one being angular momentum equals to, let me put it on the paper here. Now I want to switch radio. Okay. So angular momentum is going to be equal to moment of inertia times that guy, or for point mass, you can do angular momentum equals to R times P, which means R times mv. Okay, so this is for point mass. Okay, this is for A, this is for B. Okay, two different expressions here. So let's take a look here together. There's a few responses in already. So L is equal to I times omega. So I is equal to 1 half mr squared. So then 1 half mr squared times omega. Okay, so they are all given here. So you want to do 1 half times. So it says 16 grams, right? So you want to convert into kilograms first, times 10 to the negative 3. And then the radius says 6.00 centimeter. Okay, so you want to also convert that into meters. Okay, and then don't forget about the square here. M times the 125 radians per second. Okay, so that will give you your angular momentum as 3.60 times 10 to the negative 3 kilograms meter square over second. Okay, and then on the second part, because the motorcycle is driving with a constant speed and then that's on a circular track. So in that case, your RMP or RMV will be perpendicular to each other. Then you're going to use that equation, okay? So then L is equal to R times M times V, 35.7, that's the radius of the track, times the mass, 125 kilograms, and times the 8.92 meters per second. Okay, so that will give you 3.98 times 10 to the fourth kilogram times meters square over second. Okay, all right. So if you didn't get the number right, particularly on the first one, you probably want to do like check on the units and then also to see if you have the R squared. Okay, there. All right. So you guys can let me know anytime if you have question. Okay. So if you are clear, we are going to just move on here. All right. So we have checked on the definition of the angular momentum. So in general, angular momentum should be equal to I times omega. But if you have point mass, you can use R times M times V. Okay. If I and V are perpendicular to each other. Otherwise, you want to include a sine of theta, which theta is the angle between I and V. Okay. Now we are going to check on the dynamics of rotational motion. So in linear motion, we say derivative of momentum over t will give you net force. Okay. Now similarly, we are going to check on derivative of the angular momentum or time derivative of it. Okay. So derivative of L is equal to R cross P. Okay. That's 4-point mass. And you can see that if L is equal to R cross P, then you'll be doing derivative of R over dt times cross P plus R cross dP over dt. Okay, so two terms. Now, derivative of R over T, that will give you linear speed, linear velocity V, right? So V cross M times V, that's the P, okay, the momentum P. So if you have V cross V, for the identical vectors, cross multiplication will give you 0. So basically, this first term will vanish. Okay, so because it will give you 0, then you only would have the second term remaining. So R cross dP dt. Okay. Now, for dP over dt in linear motion, we know that's going to be equal to net force or F. Okay. So then this is going to be equal to R cross F, okay, which is the definition for the torque in last lecture. Okay, if you remember in last lecture, when we talk about torque, it's actually equal to R cross F, right? So that's the torque. So then derivative of angular momentum with respect to time t, that should be equal to torque, okay, or net torque if you have multiple forces that result in multiple torques in the system, okay. So then the second law for rotational motion would be time derivative of angular momentum equals to summation of the torques. Okay, so it will be similar to this guy here, but you are just using their angular quantities instead of linear quantities. Okay. All right. So with that, we can take a look the example here. So basically, this is dl over dt that equals to torque. Okay. So this one says a torque of 0.112 newtons times meters is applied to an egg beater. If the egg beater starts at rest, what's its angular momentum after 0.65 seconds? Okay, and then if the momentum of inertia of the egg beater is given, what's the angular speed after 0.65? So you can use the scalar form of this guy. So derivative of angular momentum over dt, that's equal to the torque given. Okay, you can do integration for this. I just realized the question was set up as multiple choice, so I just change it to short answer, so you can resubmit your responses if you have your answers. You have to click on the problem again and then resubmit the responses. All right. Anyway, let's take a look here. So starting from here, you're looking for your final L. So you can move this guy to the other side equation. So dl equals to tau dt. Okay. You are going to integrate from here to the t that's given, from here to the t that's given. All right. Or on this side, because this is the variable, so you are going to just integrate from initial to the final. Okay, initial is 0, final is the what you are looking for. So then L should be on this side minus 0, okay, because it's just constant 1 here, so it will be L minus 0. That equals to tau times, tau is constant, times t, all right, from 0 to t, that's given. So L will be tau times t then. Tau is given as 0.12, t is given as 0.65 seconds. Okay, so then it would be 0.078 newtons meters times second. Okay, you will figure that this is equivalent to kilogram times meter square over second. Okay, so either way. All right. And then the second part, if the moment initial is given, so if I is given, then you're looking for what's the angular speed. Okay, so that's the final speed. This is 0.078 on this guy, newtons meters second, equals to 2.5 times 10 to the minus 3 kilogram times meter square times omega. Okay, so omega will be equal to 0.078 divided by 2.5 times 10 to the minus 3, okay, which will be 31.2 radians per second. Okay, that'll be your final angular speed. All right. Let me know if you have questions. So if not, then we are going to take a look if you have a system of multiple particles, and so then the overall angular or total angular momentum should be summation of the angular momentum from each of the particles. Okay, then for the derivative of the total angular momentum, that should be equal to summation of all the torques on each of the particles. Okay, so that's what will happen there. Okay, so it will be similar expression for the one we saw earlier for a point particle. Okay, but just summation of them all over together. Okay. Um, Next section here, we'll be talking about conservation of angular momentum. Okay, so similarly, when we talk about linear momentum, then later on we talk about dynamics of moment of the object, and then by looking at the time derivative of momentum, here we'll be looking at then the conservation of angular momentum. Okay, so similarly, if the net torque is equal to 0, okay, so tau is equal to 0, then delta L over delta T should be equal to 0, or that's will tell you delta L is going to be 0. Okay, so that means the angular momentum is conserved. Okay, so for one example here, you guys can do this by yourself if you are having a chair that can rotate. Okay, so you can manage it to have an initial rotational angular velocity. You can extend your arms. You don't necessarily have to hold two weights. You can extend your arms and your legs. Okay, and then maintain a angular speed. You can ask your roommate to help you, just spin you up. Then if you pull your arms and leg back to your body, you'll see that the rotational speed will increase. Okay, so during this process that you pull your arms and legs in, the forces on your body is just your external forces. Okay, so then the torque as a result should be equal to 0. Okay, so angular momentum is conserved in that case. So what happens is when you are having your arms and legs extend out, the overall mass of your body is more stretched out. Okay, so then the overall radius for each part of your body is going to be larger than you pull your arms and legs in. Okay, so then moment of initial in this scenario, you have your arms and legs extended. It's going to be larger than the moment of initial when you have your arms and legs pulled in. Okay, so your moment of initial will decrease, then your angular speed will increase. Okay, so that gives you the same angular momentum. Okay, and similarly, if you guys have watched like figure skating, a popular move that the skater do is when they are spinning initially with their arms and one leg extended. Okay, then what they typically do is they pull their arms and legs in. So then their spinning speed will be increased due to that, because in this configuration, when they have arms and leg extend, they have more moment of inertia. When they have arms and legs pulled in, they have less moment of inertia. So to keep the angular momentum the same, they have the angular speed or angular velocity has to increase. Okay, so then they can spin faster. Okay, let's take a look this example here. It says as an ice skater begins a spin, her angular speed is about 3.04 radians per second. After pulling in her arms, her angular speed increases to 5.24 radians per second. Find the ratio of the skater's final moment of inertia to her initial moment of inertia. Okay, so you're looking for I final over I initial. Okay, you are going to use the um, conservation of angular momentum, Li equals to Lf. That means um, I initial times omega initial equals to I final times omega final, right? So it should be quite straightforward for you guys. All right, so we can take a look here. So basically, you're going to use this equation and you're looking for that guy, right? So you're looking for IF over II. So you're going to just isolate that. Divide both sides by II. We'll get rid of II on this side, okay? And then divide both sides by WF, omega final, or omega F. Then we'll get rid of this, okay? So then your IF over II is going to be equal to omega I over omega F, okay? So which is 3.04 radians per second divided by 5.24 radians per second, okay? That will give you roughly 0.580, okay? So that means the final moment of initial is about just only 58% of the initial, okay? All right. So we are going to take a look on a second example here. This one says 3 children are riding on the edge of a merry-go-round. You can treat it as a uniform disk. So then moment of initial again will be for a uniform disk is going to be 1/2 mr square. Okay, and it says has a 1.60 meters radius and is spinning at 20.0 rpm. The children have masses of 22.0, 28.0, and 33.0 kilogram. If the child who has a mass of 28 kilogram moves to the center of the merry-go-round, what's the new angular velocity? Okay, so during the process, the moment of initial of the system changes. Okay, so you have to treat the merry-go-round and the 3 children as one system, and then initial and final. Okay, so initially the children are on the edge. For the final status, one of the children moved to the center of the merry-go-round. So that um, changes the moment of inertia. Okay, so I will have you guys give it a try. We can take a look on this one together in a few minutes. Okay. All right, so let's take a look here. So during the process, when one of the child moves to the center of the merry-go-round, so the interaction will be just between that child and the merry-go-round. So the forces, you should consider them as the internal forces. So then there will be no external torque on this on the whole system, right? So then um, torque is equal to zero or external torque is equal to zero, then angular momentum should conserve in this case. Also, again, Li is equal to Lf. Okay, initial moment inertia is equal to final, or initial angular momentum should be equal to final angular momentum. Then I omega I should be equal to If omega F. Okay, so you are given initial omega, you're looking for this guy, right? Then you also need to know the initial moment of inertia and then the final moment of inertia. Okay, so let's take a look, see what's I and then what's I final. Okay, so I, because you have the merry-go-round, will be 1/2. Let me use the capital M times R square. Okay, it's a uniform disk plus the moment of initial for each of the child. We can treat the child as point masses, so there will be M1 R square because they are sitting on the edge. Okay, M2 R square and then M3 R square. Okay, so you can actually single out the R squares and then combine the rest together. So 1/2 capital M plus M1 plus M2 plus M3. Okay, times R square. So that's 1/2 times 100 kilogram plus the 22 kilogram plus the 28 kilogram plus the 33 kilogram, okay, times the radius of 1.6 meters square. So that will give you 340.48 kilogram, okay, for II. For IF, you're going to do the same here. So 1/2 or similar like capital M R square plus M1 R square plus the M2. So this child moves to the center of the merry-go-round. So that means the radius for this guy is 0. Okay, plus M3 R square. Okay, so it's going to be similar to here, but the second turn, the second child have moment of inertia equal to 0. Okay, so it's going to be 1/2 capital M plus M1 and then just plus M3 times R square. Okay, so 1/2 times 100 kilogram plus 22 plus 33 times 1.6 meters squared. Okay, so in that case, it turns out to be 268.8 kilograms times meter square. Sorry about that. It should be kilograms times meter square on the first initial moment of inertia as well. Okay. Draw a dashed line to separate the two. All right. Then you're going to solve for your omega now because now you have everything else needed. Okay. So omega final. To solve for omega final, you want to divide just everything by IF. So omega initial um I initial omega initial divided by I final. Okay, so it'll be 340.48, okay, times the 20, I believe, RPM. So in this case, it's expressed in RPM. Okay, so that's fine. This guy is 268.8 kilogram times meter square. The same as this guy. Okay, so these two units will cancel out. It's going to be 25.3 RPM. Okay, RPM stands for revolutions per minute. Okay, and the responses you guys submit in are correct. Okay, that's great. All right. again, if you have questions, you can let me know. Okay. If you are clear, then we are going to move on here. Okay, so next we are going to look at the collisions during a rotational motion. Okay, so for example, so you guys probably haven't seen or likely haven't seen a, a player, video player like this. It's like you have a like CD and then the CD player with a turntable. Actually, you can yeah, put this guy in and then it will play music, okay, with a reader. But this is what happens. Okay, so the turntable will have initial angular speed omega 0, and then this guy will be starting from rest when it's released. Okay, then it will collide on the table here, and then briefly, momentarily, they will have the same angular velocity. Okay, so the system, if you look at the system of the CD and then the turntable, okay, should have conservation of angular momentum because the interaction between them are internal, like the internal forces between them, and then the torque should be equal to 0. External torque should be equal to 0. Okay. So then in that case, angular momentum should conserve. Okay, just as what we did for linear collision, it should conserve as well. Okay. Another type of collision is like this. So if you have a meter stick, right, and then if the one end is or just anything like a stick, like probably maybe not as long as 1 meter, but could be anything, or a ruler maybe, with one end being fixed, but can rotate with that fixed point. Okay, so then it's pivot at that point. Now, if you have a small object, you can consider that as point mass storm towards the other end of this. So after the collision, if these two, the small mass is sticking to this piece of say ruler, then they will rotate with this x rotation. Okay. So then in this case, it's a collision, but rotational collision. So you can also apply conservation of angular momentum here. Okay, so initial momentum should be the initial angular momentum of this point mass. Now for this ruler, it's stationary, so its initial angular momentum should be 0. But after the collision, these two will share the same um, angular velocity. Okay, so then you can calculate what's the final angular momentum by calculating the moment of inertia multiplied by its final angular speed. Okay, then that should be equal to the initial moment of angular momentum of this point mass, which will be like r times m times v. Okay, so on that one, let's take a look on this guy here. Okay, so I think I'm gonna to just show you guys the solutions because we are kind of running out of the time here. All right, so let's see. Maybe on this paper, that should be enough. This one says a student sits at rest on a piano stool that can rotate without friction. The moment of inertia of the student stool system is 4.1 times kilogram times meter square. A second student tosses a point mass of 1.5 kilogram with a speed of 2.7 meters per second on to the student on the stool, who catches it at a distance of 0.45 from the x rotation. What's the resulting angular speed? Okay, so let's see. So a student is sitting on a stool, piano stool, which can rotate. Okay, so this is like 0.4 meters. He'll catch that point mass that's moving in that direction. V equals to 2.7 meters per second, mass equal to 1.5 kilogram. Okay, and then this is R as 0.40. So initially, a student is at rest, is asking you what will be the resulting angular speed. So after the impact, this guy will rotate, right, in this direction, omega. All right. So again, so this is angular collision over here. So then we can apply initial angular momentum equal to final angular momentum. Initial angular momentum will be just RMV, okay? Because it's the point mass. Initially, student and stool are at rest, and then just will be just from here when it's caught, okay? And then that should equal to I of the student stool plus the mass times the omega, the final omega, okay? So R and V are given, and we are looking for omega, so we need to figure out what's the moment of initial for the student stool and the point mass combined, okay? I think it tells us the moment of initial for student stool to be 4.1 kilogram times meter square, okay? So then this guy will be just adding moment of initial for the point mass, okay? So I student stool with the point mass should be equal to I student stool plus the point mass, which will be mr square, okay? So 4.1 plus 1.5 times 0.4 meters squared, okay? That would be 4.34 kilogram times meter square, okay? So then you can solve for your omega. So your omega then will be RMV divided by I moment of inertia for the student stool plus the point mass, okay? So 0.4 meters times 1.5 kilogram times the velocity or the speed 2.7 divided by 4.34 kilograms times meter square, okay? So this will give you your final angular speed as 0.37 radians per second, okay? All right, I'm going to pause a few seconds to see if you guys have questions on this. All right. If not, then we'll move on to the next section here, the gyroscope. So a gyroscope is a piece of device like this. So if you give this guy initial spin, like a very large angular speed, okay, angular velocity, then you can actually let it process on the table. It will not fall down for probably quite a few, like quite some time, okay, maybe a couple minutes or maybe like 10-20 seconds or so, okay? So when that happens is because there's angular momentum of this guy here, okay? So we are going to just take a look at a couple videos here. Let me just, I'll have to reshare. Start sharing this one here. Wait a second.
When I hold the spinning wheel, nothing crazy happens. But when I flip it, I spin. Flip back, and I stop. Flip it, I spin. So the question is, why am I spinning? So I have to force the wheel to turn over. Now Newton's third law says that for every force, there's an equal and opposite force acting as well. So when I force the wheel is applying force equal and opposite onto me, causing me to turn. So the same thing applies when I'm on the ground, but the friction between my shoes and the ground stop me from spinning. So another way to explain what's going on is through conservation of angular momentum. Now, angular momentum is something that tells you how hard it is to either start or stop something from spinning. And it depends on two things. One, how fast it's spinning. We call that the angular frequency. Two, its shape, or what we call the moment of inertia. So this wheel is rotating counterclockwise. Now I'm going to teach you a trick. So get your right hand, and I want you to curl your fingers in the counterclockwise direction. And you see that your thumb is pointing upwards. We'll call that the positive direction. So see, this wheel has positive angular momentum with a magnitude of L. Angular momentum is conserved. That means that as long as there are no outside forces, the total angular momentum of the system always stays the same. So when you flip this thing over and do the right hand trick, your thumb points down or in the negative direction. So the angular momentum of this wheel is now negative L. So the whole system, me, the turntable, and the wheel starts out at positive L. But when you flip the wheel now has negative L. So the whole system needs to stay at positive L because of conservation of angular momentum. So I need to spin with angular momentum of positive 2L. That's why I spin the other way.
And then there's a second one. Just spare for a few more seconds. All right, so I think that's the ad is being played. Wait a second.
Hey everyone, it's me, Derek, from the channel Veritasium. And I've been following this series by Destin on Smarter every day about helicopters, and gyroscopic precession is just one of those things that still blows my mind as it did Destin's. So I'm here at the University of Sydney, my old stomping grounds. I'm going to borrow some of their lecture dem equipment to hopefully teach you a bit about how gyroscopic precession works. The first thing I need to do is talk about vectors, because a lot of things in physics are vectors. That means they have direction. So an example would be momentum and force. Those are two examples of some pretty common vectors. So if I have a cart moving along here, it has some momentum in that direction, and if I apply a force to it, I can change its momentum. So for example, if I push it to the right, then its momentum will increase to the right. It all makes a lot of sense. Well, there's a similar statement we could make about rotating bodies, which is that a torque increases the angular momentum of an object in the direction of that torque. So let's try to figure out those terms. If I apply a force down on this side of the wheel, I create a torque. Now, torque is force times the distance from the rotating axis. You could call it R. So torque is the force applied times the radius away from the turning axis. Now, what's the direction of that torque? Well, we actually use a right-hand rule to define this. And so what you do is you put your fingers in the direction of the radius from the turning axis and curl them in the direction of the force, and your thumb points in the direction of the torque. So the torque is actually out this way at 90 degrees to the force. The force is down that way, but the torque vector is actually pointing out this way. So the angular momentum of this wheel is being increased in that direction. So the more I apply this torque, the more I increase the angular momentum of the wheel in the direction of the torque. So I'm making this wheel have a very large angular momentum out towards the camera, out towards you. Now, before I go any further, let's have a look at this setup that I've got. I have a wheel here hanging from only one side by this rope. And so right now there's actually a torque on the whole system if I let go, because the weight of this wheel is pulling down, and that force is applied at this distance away from its pivoting point there. So if I let go, well, it does exactly what you'd expect. The wheel swings down this way. But I want to see that as an example of rotational motion. There's a torque which is pointing out this way, which is trying to increase the angular momentum of the system in that direction. Now, angular momentum in that direction requires that the whole system starts swinging anti-clockwise. And so that is what happens. But what happens if I only let go after I've already spun up the bicycle wheel? Well, in that case, the bicycle wheel would already have angular momentum this way, and so a torque pushing that way actually swings this angular momentum around that way. Okay, so let me try to get the wheel spinning and make it work. Come on. Oh, look at that. It's rotating as we predicted. See, the angular momentum vector is pointing out this way, but torque is pushing it this way. So angular momentum, torque, and torque is pushing that angular momentum vector around. Except not for long, because this appears to be a quite frictionful wheel. So check out Destin's other videos about helicopter physics, and then come check out my channel, Veritasium, where you can find more like this. Except I don't often nearly get.
Right. Sorry that I ran over a couple of minutes, but that'll be it for today. Okay. I'll see you guys on Monday's lecture.
All right. Thank you. Have a great day.
All right. You're welcome. Bye.